Problem number 19. Consider the surface S consisting of the part of the cone z is equal to 6 minus the square root of x squared plus y squared above the plane z is equal to 0 together with the disk at the base. Let's just draw a quick sketch here so we can see what's going on. So our region here, our surface, it consists of the side here, the side of the cone together with the base. It consists of both parts of that is S. So suppose we were interested in finding the flux of the vector field across S. Okay, we computationally, notationally speaking, we are being asked for this quantity here. Well, we could do it, but it would be a little bit of work because we'd have to do one surface integral pointing straight down from the base of the cone. We'd also have to do a second surface integral pointing out from the side of the cone. And those might be a little bit of work here. So fortunately, what the divergence theorem tells us is that we can instead compute this triple integral here, the triple integral of the divergence of f over the region W, where W is the region inside of our cone here. So let's do this instead. Okay, what is the divergence? The divergence of f is equal to, okay, the partial derivative of this respect to x is x squared. The partial derivative of this respect to y is y squared. Okay, so this is the region, this is the integrand here. Okay, so for part B, right, but do not compute a triple integral in cylindrical coordinates, which gives the flux of f. Okay, so how do we represent the region inside this cone in cylindrical coordinates? So we're going to have bounds on r, theta, and z. So let's see here. We go one loop around the circle. Theta runs from 0 to 2 pi. Z, the smallest z can be a 0. We go until we hit the side of the cone, 6 minus the square root of x squared plus y squared. And then r, I made one mistake here. Should have been paying more attention to this. Of course, we need to convert to cylindrical coordinates here. Square root of x squared plus y squared in cylindrical coordinates is just going to be r. Okay, how about this? The smallest r can be here is 0. The biggest r can be, well, remember r is going to be square root of x squared plus y squared. This boundary curve right here, so that would be, that's the intersection of z is equal to 6 minus x squared plus y, square root of x squared plus y squared, with z is equal to 0. So solving this equation, but this square root here of x squared plus y squared is just r, so the biggest r can be is 6. Okay, so we've got all of the bounds here. So now the last thing to do is equal to the triple integral. Theta runs from 0 to 2 pi. And then r runs from 0 to 6. Z runs from 0 to 6 minus r of x squared plus y squared. Of course, that becomes r squared. Throw in the factor of r. We still need that dz dr d theta. Okay, that is problem number 19. Let's take a look at problem number 20. Okay, so similar feeling thing. Now instead of a cone, this is a paraboloid. So the picture is still going to look, kind of the same here. In the first octant, we're also told that. So it's not the entire part of the paraboloid. First octant means x, y, and z are all positive, or I should say non-negative more precisely. And so then C is the boundary curve here. So this is our C. And let me get a different color here. That right there, this is our S. Okay, so how do we go about doing this? Okay, parametrization in terms of coordinates x, y, and Cartesian coordinates or cylindrical coordinates. I'm going to use Cartesian coordinates here because this is graph of a function. R of x, y, our parameterization is x, y, and then z is 6 minus x squared minus y squared. Why do we choose that? Because part B is asking us for the r sub x cross r sub y, and we can just read that off of this chart right here. So we end up with the negative of the x partial derivative of this. So the x partial derivative is negative 2x, so this becomes 2x. The negative of the y partial derivative is 2y, comma 1. Okay, so this is our formula for this cross product here. We should also at this point take a moment to say what are the bounds here on x and y. So we certainly have both x and y have to be greater than or equal to 0. In the xy plane, so, projecting this down to the xy plane, looks like this. This curve right here, this is when z is 6 minus x squared minus y squared is equal to 0. So this is, 6 minus x squared minus y squared is equal to 0, where x squared plus y squared is equal to 6. So the allowable bounds here, let me put them inside this box. X and y are both non-negative, but also x squared plus y squared is less than or equal to 6. Okay, so that's part A and part B. Part C is asking us to find the curl of this vector field here. I bet we're going to do a Stokes theorem, coming up pretty soon. Okay, curl of F, I hat, j hat, k hat, d by dx, d by dy, d by dz, yz, negative xz, and 1. So what do we end up with? Okay, it's the I hat component's going to be the partial derivative with respect to y of 1, that's 0, minus the partial derivative with respect to z of negative xz, so that's negative x. Then the partial derivative with respect to z of yz, it's y, minus the partial derivative with respect to x of 1, that's 0. And then the partial derivative with respect to x of negative xz, it's negative z, minus partial derivative with respect to y of yz, that's also negative z here. Okay, so let's see, this ends up as, I didn't botch up anything, x, y, negative 2z. Okay, so that's part C. How about part D? Use Stokes' theorem. I put that away in my scrap pile. I should keep it a little bit closer at hand because we're probably going to use it in part D. Use Stokes' theorem to write double integral in polar coordinates, which computes the work, the circulation F along C. So Stokes' theorem tells us that, okay, this is C here, the boundary. Circulation at F along the boundary C here is equal to the double integral of the curl of f over s itself here. Okay, so let's not do 1, 2, 3 separate, vector line integrals. Let's do a single surface integral instead. And this is going to give us, okay, so the curl of f is right here, x, y, negative 2z, dot product with the normal vector d sigma over s here. Okay, well, and so, well, at this point then, we're being asked for polar coordinates. What I'm going to do is I'm just going to do it in rectangular coordinates for the time being and then switch to polar coordinates at the end. Okay, so this is our parametrization for the surface. And we already have the normal vector, that's good. We need to take this, let's see here. We're going to substitute in our parameterization into the integrand here. So that's just going to be x is x, y is y, negative 2 times z we replace with 6 minus x squared minus y squared. And then we'll do a dot product of this. This is f of r of x and y. Going to do a dot product of this with the normal vector right here, which is 2x, 2y, and 1. So what do we get? X times 2x is 2x squared. Y times 2y is 2y squared. And then we have 1 times this. So there's a negative 12 minus 2x squared. Oops, negative times negative is plus 2x squared plus 2y squared. So what is this? 4 times x squared plus y squared minus 12. So we're going to be integrating this over the region that x and y are both greater than or equal to 0. X squared plus y squared is less than or equal to 6. So let's finally convert to polar coordinates. This region right here in polar coordinates, theta is running from 0 to pi over 2. R is running from 0 to the square root of 6. And so our integral is theta from 0 to pi over 2, r from 0 to square root 6, 4r squared, let's convert that to polar, 4r squared minus 12 times the r, we convert to polar, so we need to throw in the r d theta. And that is our final answer to part D.